Hello everyone, I'm Conor Kennedy, and today I will be presenting to you the USACO Open 2023 Silver Problem 1 Milk Sum. In this problem, Farmer John has some cows, each with a different milk production value, and each of these cows gets a different amount of time hooked up to the milking machine before they get sent out for their exercise routine. One cow has 1 minute on the milking machine, another cow has 2 minutes, etc., all the way up to n minutes. We want to find the optimal amount of milk that can be produced. So, for example, in this case, we have a cow with 1 milk production value, a cow with 10, a cow with 4, a cow with 2, and a cow with 6. This is the first sample case. And uh, to optimally get the most amount of milk from these guys, we give this one 1 minute, give this one 2 minutes, give this one 3 minutes, give this one 4 minutes, and give this one 5 minutes. And if we do this, we get a total milk production value of 91, which is optimal in this case. But that's not all for this problem. Farmer John wants to know what happens when various changes are made to the cow's milk production values. For example, when this 10 is changed to a 1. In this case, the optimal milk production changes, and we have this new arrangement of waiting times, and we get a total of 55 at the end of this change. So how do we solve this problem? Well, first let's look at the problem without any changes. So the problem would be we're given some number of cows, and we want to find the optimal milk production for those cows without any changes. Well, I claim that a simple greedy algorithm will suffice, where we simply give the cow with the greatest production value the most amount of minutes, the cow with the second greatest, the second most amount of minutes, and etc., all the way down to the cow with the least milk production value, 1 minute. And the reason that this is optimal is if we didn't do this, like for instance, we gave one cow with this lesser milk production value a higher amount of minutes, it would always be more optimal to swap these instead. So giving 9.5 and 8.4. In this case, that gives a higher production value of 77 instead of 76. So with our greedy algorithm, all we need to do to find the optimal arrangement of milk values is to first sort the numbers. So in this case, it would be 1, 2, 4, 6, 10. And then assign those the minutes 1, 2, 3, 4, 5, and so on if there were more cows. And then we can multiply these together to get the total amount of minutes, which in this case is still 91. So that's the problem without changes solved. But how do we solve the version with changes? If we just try performing this algorithm for every query for every change, that would be much too slow, since we have 10 to the 5 cows and 10 to the 5 queries. So with a algorithm where we execute this for every single query, then that would take at least OQN time, which is already too slow. So how do we work with these queries in a more efficient way? Well, let's look at what happens when one of these queries happens. Take this case, for example, where you have these 6 cows. I put them in already sorted order, but if they're not in sorted order, then you can just sort them. The optimal production value for this one is where you give 1 minute to the first cow, 2 minutes to this one, 3, 4, 5, 6, etc. And this gives us the milk production value of 155. But let's say that this cow that used to have 9 is now changed to 2. What would happen to the milk production? Well, the different number of minutes we give are now changed. So we now give 1 minute still to the first cow, but we give 2 minutes to this one, and all of these ones go up by 1, except for the last one. So with these new allocation of minutes, we now have these new production values, resulting in a total of 129. But let's look at how they changed. We see that the new position of the cow now contributes 4 to the total. Each of the positions in between now increase by the values of the cows at those positions. And then the position that we removed gets removed completely. So maybe if we're able to calculate these changes in a meaningful amount of time, then we're able to solve the problem efficiently. Let's try and generalize what we saw there. So Let's consider a case where we don't really care about the other cow's values. So those are represented by dots. And we have this cow x that is being changed to a new value of y. Let's give these some indices too. Let's say x is at index j and y is at index I. Note that these indexes actually correspond in a sorted list to the amount of minutes that we give each cow. Actually, correction. Let's say, since y doesn't exist yet, we can't assign it an index at first. So let's say it gets inserted right before cow at index I. So the cow before y is I minus 1, and the cow after is I. Let's see how the movement from x to y changes all the indices. All of these indices still stay the same, except for when we get to y, because now this is going to be the new index I. And all of these get moved up one index, so this gets to I plus 1, I plus 2, etc. All the way up to j minus 2 still, j minus 1. And now position j, actually hang on, this shouldn't be j minus 2 since these are all getting moved up by 1. So this is j minus 1, and now this is the new index j. And then this cow doesn't exist anymore, and now this is j plus 1, j plus 2, etc. So only the cows inside this range from I to j actually get changed. And since all the indices in this range get increased by 1, we can actually easily calculate by how much the milk amount changes when we add 1 to each index in this range. And since we're adding 1 to each index in the range, we're essentially giving each of these cows 1 more minute. And by giving each of these cows 1 more minute, we're essentially adding on to our total the sum of the cows in range from I to j minus 1. And our other two changes here are when we remove this j. So we have to subtract j times x because there used to be a cow with milk amount j, and now there isn't. And we have to add over here y times I, or IY, I guess. So now we have a general formula for how to calculate our change. So first we add on IY, then we add the sum in this range from I to j minus 1, and then we subtract off jx. So now the difficult part is finding how to get this sum in the range quickly. Because in the worst case, this sum could be the sum of n different cows, which is going to be too slow if we try to do that for every query. And an efficient way to do this kind of range sum query, especially when the array doesn't change, like these cows never get changed, only this individual one does, and like it gets put back after the end of the query. So a quick way to do these kind of queries is using a prefix sum. A prefix sum is just a handy array that lets you quickly calculate the sum of a prefix. And what that means is that an index I of the prefix array, it corresponds to the sum of the first I elements. So the first index here would correspond to the sum of the first element, which is just 1. The second index would correspond to the sum of the first 2 elements, so that would be 3. And then continuing on, we had 7 here, we had 13 here, and we had 23 here. And this is our prefix sum array. You can see how prefix sum arrays could be useful because they allow you to quickly get the sum of an entire prefix of the array. But there's actually a trick that you can use to get it to be range sums instead. Say we wanted to get the range 4, 6, the sum of this little range. And if we look into our prefix sum array, we can see that this value corresponds to the sum of this entire range. Or this entire range. However, we have some extra elements here, but we can get rid of these extra elements here by simply subtracting off this prefix sum. So that'll subtract off this prefix sum, and that'll leave us with our desired range of 4, 6. So to get a range sum in the prefix sum array, all we have to do is we take the upper end of the range, take the prefix sum value there, and then subtract off the prefix sum with the lower value. So if we wanted the range I to j, then we take prefix of j, and then we subtract off prefix of I minus 1. I'm going to make a slight modification to this for this problem though, just to make something simpler. I'm actually going to use a suffix array. A suffix array is just the same thing, except we start from the other side. So we would start with 10 here, and then for the last element, and then the second one would be the last two elements, so 16, then the last three, then the last four, so this would be 22, then the last five, 23. This is equally as powerful as a prefix array. It's just that we have to think of our range a bit differently. In our suffix array here, to get the sum from the range I to j, we take suffix of I and subtract off suffix of j plus 1. Since that would be taking the last I elements and then subtracting off the last j plus 1 elements, instead of the first j elements minus the first I minus 1 elements. And the only reason I want to use a suffix array is because it makes our calculation of the initial answer somewhat easier. Because we can represent the number of minutes here, 1, 2, 3, 4, 5, and the number of milk production values as just repeating the milk production values a certain number of times. So repeat the first one once, the second one twice, the third one 3 times, fourth one 4 times, and the last one 5 times. And if we look here, we see that this last value is just the last number of the suffix array. This here is the sum of the last two elements, which is the second to last element of the suffix array. This one here is the last three elements, so which is the third number of the suffix array, and etc. So this one's 22, and this one is 23. So we can see to get our answer, if we just sum this up, we get 91. And to get our answer, it's just the sum of every element of the suffix array. So using the suffix array makes the initial answer computation easier, so it isn't really much of a difference over a prefix array after that. So let's see how we can apply this suffix array to make this part of the problem easier. So if we want the sum in the range from I to j minus 1, we can just look at this formula, and this will tell us that the sum from I to j minus 1 is equal to suffix of I minus the suffix, and here it's j plus 1s, but since we want the range from I to j minus 1, this is actually just suffix j. So that's how we could quickly calculate the range sum, and this will speed up queries significantly. Note that we've actually only covered one of two cases though. In our previous case here, we were starting from a higher value and going to a lower value. But if we start from a lower value and go to a higher value, that's actually a completely different case. So let's see what happens to our indices here. Let's say we have our old one at index j, and our new one right before the index I. So we have our indices j minus 2, j minus 1, and then going up to j, and then going up to I. So what happens when we perform this change? So all of these stay the same down here, still j minus 2, j minus 1. This one is no longer index j since it's get removed, so this one actually becomes index j, and then this is j plus 1, and then we continue on, and this becomes I minus 3, I minus 2, since we are shifting it down by 1 all over the place. This becomes index I minus 1, and then these stay the same, so these are I plus 1, etc. So these are our new indices. So we see that all the indices in this range get decreased by 1, which is different from our old case where they are all increased by 1. So in this case, instead of adding on the sum of this range, we need to actually subtract the sum of this range. And this range is actually a little bit different. This is the range, sum of range from j plus 1 here, all the way up to I minus 1. That gets changed. And we also still have our original changes here, where we have to subtract off xj, and we have to add on I minus 1. And notice that this is I minus 1 instead of yi. And as before, we can represent this sum of range using a suffix array method. So if we take suffix of j minus 1, or j plus 1, and then we subtract the suffix, and since this is I minus 1, if we plug that into here, we get I plus 1 or I minus 1 plus 1. So this just becomes suffix I. And notice how this is suffix j plus 1, and over here is suffix I without a plus 1. So it's slightly different. There's one final case where the number actually stays the same. We could handle this separately, but notice that if we actually just keep it the same, if we just use the code for this case, then this sum of range will be empty. I'll subtract off the new value and add on the old value. So it would actually be equivalent. And actually I'll use this uppercase here just because it has some less weird stuff. There's one thing that I've kind of glossed over here, which is that we don't actually know these indices of the new location. So we don't know like this value of I. So we have to find it ourselves. And we have to find it in a smart way because if we just look through the array until we find it, that could take up to O(n) time, which would make our runtime too slow. So the way you can find this is using binary search. You simply, since we want to find the new location in the array, we can binary search for the first element that's greater than the new value, y. So if we binary search for that, then that reduces our runtime to, or our search time to log n. And overall, this strategy here, if the binary search will take log n time, this summa range is constant time since we're just looking at these arrays. And so for each query, then we have a log n time for each query, which gives us a total runtime of q log n, plus n log n for initial sort. So that is fast enough to pass. So let's quickly summarize our solution. First, we sort the array, though do be careful to keep the original array around because that's what we need to use to find like what the queries are referring to. Next, we create our suffix array, and we can just do this by using a for loop over our sorted array. And in the process, we find the sum of the suffix array to find the original answer. Now we want to loop over every query, and we want to find the indices ij of the elements in the query. And now we want to split into cases, case where I is greater than j, so the value has gone up, and I is less than j, where the value has gone down. And finally, using the formulas we found for each individual case, we can find the change, and then we just add that to the original answer and output our answer. So yeah, that's the idea of the solution, and let's look at our code for it. So here's my C++ code for the solution. So we first start with reading in our input here. Note that I use long longs, or Java longs, so that my value doesn't overflow. Then I create a copy of the array by just passing in the value of a, or the vector a, into this vector. And then we sort the array, so this is just our sorted array. So now here's where I compute the suffix array. I make it of size n plus 1, just giving it some extra buffer room at the end, because it's possible that our query uses the suffix past the end of the array. And you have to be careful of this when doing prefix sums too, because since prefix sums uses I minus 1, if I is 0, then you can potentially index into -1. So it's better to make it one index usually, so to avoid those kind of problems. But in this case, since I'm using a suffix array, it's still 0 indexed. I just add on an extra element to the end. I also keep track of our answer here, so I loop through the array, and the way you calculate the suffix array is first you add on the previous suffix, or I guess the next one, and then you add on the current value of the array. So the suffix array just kind of builds off of each other. And then we add on the suffix array there to get our total answer, which is just the sum of every suffix element. So now we read in the number of queries, and we loop through each query. So we read in the index and the new value, and here's where I find the I and j. So new in here represents the I, which is just the index of the new position, or rather one past the index. And to do this, I use the C++ lower bound function, which is able to find the index of, or it returns a pointer, or the iterator, pointing to the elements that compares at least to the equal of new v. So in this array, it finds the value the first value that is equal to or greater than this one. And to get the index from that, I just subtract off the iterator corresponding to the beginning, and that gives us the index. And remember that these are 0 indexed, whereas in the original problem, it's 1 index, so some of these formulas are probably slightly different. We also get the old index. You can do this by having a lookup table instead, but I just chose to do another binary search. And if you're in Java, I think there's array.binary search, or you can also just do a manual binary search to look for the element. So I just look for the array. I use in -1 because remember we're still 0 indexed. And then I subtract that to get our index. So now I do our changes things. So if new end is less than or equal to old end, and this is the case where the value decreases. So we first do the suffix change. So this is the change where we subtract or we add on the value since the values are getting increased. And then we do our change here where we subtract off the old index times the old value. And then we add on the new index times the new value. And note that these are +1s because, again, we're using 0 indexed here. In our other case, where the new index is greater than the old index, this is the case where the value increases. So we subtract the suffix from the old index +1 to the new index, and then we subtract the old index number of minutes, and then we add on the new index times the new number of minutes. And after these changes, the current will store the answer for this query. So we just print that out, and that's it. So yeah, that was my solution for the Open 2023 Silver, problem 1. Thank you for watching.